This will be the last example for our topic of magnetic circuits. This is a little lengthy example, but I hope if you will try to follow with me, it will become easy for every single one of you. So let's look at this core. Now we have to divide this core. We have a source on the one side, and we see that the flux is being produced. Flux comes here, and the flux gets divided at this point. So the reluctances are now not in series, all the reluctances. Then the flux that is on the right side, it is the same flux that travels up to here from point, and then what happens is new flux come here, add to it, and the flux goes like this. So by the flow of flux, we can see that from this point to this point, same flux is flowing. Okay, so this part is actually one reluctance. And if you look at this from this point to this point also, if you imagine, one flux is flowing, so this is also one reluctance. And if we look at from this point onwards to this point, same flux is flowing. So these are the reluctances. There is not one reluctance here, there are two reluctances, but they are also in series. So to make it more direct, let's see. From this point onward to this point, I say we have a reluctance R1. And from the center, if you look at the center point, the center leg, we have two reluctances here. We call them R2 and R3. You'll say, why two reluctances? One is of the core and one belongs to the air gap. So for the core R2 and for the air gap R3. And lastly, for this part of the core, we can say that we have another reluctance. We call it R4. Now the question then comes, how will be the equivalent magnetic circuit for this circuit? So we can see that we have one source, and then there will be one reluctance R1 that is in directly series with the flux coming out from the source, right? After that, our circuit gets divided. It becomes two part. Then for this red marked part, we have one reluctance here. We can call it R4. And in the center part, in the center leg, we have two reluctances, R2 and R3. R3 is from the air gap, R2 is the core. So this is actually a circuit, a little bit complex electrical circuit that you have solved recently. Now it is simply in the form of magnetic circuits, but the rules are the same. And what is the question? What flux exists in each of the three legs? First, they want to know what are the reluctances that exist in all the three legs. One will be what flux exists in this leg, and this leg. What is flux density? Assume the effective area gap due to fringing. So we have also a fringing effect acting here. So we need to calculate the flux here. F flux T is actually the flux that is flowing through the left side. What will be the center flux? It will be the flux divided here, and to the right side will be the flux on the right side. So first of all, to calculate the flux T, we have to calculate RT. Now to solve the circuits like this, we know that these two branches, let's change the color. We know that let's make it a simple circuit for two parallel resistances like R1 into R2, R1, R2. So their equivalent resistance will be R1 into R2 divided by R1 plus R2. And this will become the equivalent of two parallel impedances. And if we have an impedance R3 here, so total R equivalent will become, here we have R3. Let's not confuse you guys. Let's see. Now if we have a circuit like this, here we have R3, this. So if this is I call Rx, this is R1, this is R2, we find the equivalent of this, and it will become RT will be Rx plus the R1 into R2 divided by R1 plus R2. This is basic circuit theory. So to calculate RT, it will become, for our circuit, we can calculate RT. This is actually equals to R1 plus these two are in series and this. So this will become R2 plus R3 into R4 divided by R2 plus R3 plus R4. This is how we can calculate the value for RT. Now once we have RT, we can calculate the total flux and all the other fluxes. So next question comes, how to calculate these reluctances. And to calculate these reluctances, let's see. R1 we know is on the left side. R1, the length you can calculate, it is 25 centimeter plus 7.5. And here how much? It will be 4.5. So we have 25 and then so this will become 37, and this will also become similarly 37, and this side will then become 25. This side will become, we have 25 up to here, and then we have 4.5 and 25 up to here, 25 up to here, and then we have 4.5 and 4.5. So this will become 34. Okay, so this was 37, and this length will be 25 and 9, that is 34. So the length L1 over mu over A1, this length will be, then easily we can say it is 37 centimeter top side plus 37 centimeter bottom side plus left side's length is 34 centimeter. So this will become 108 centimeters, that is equal to 1.08 meters. The next is area. Area A1 is 9 centimeter and to 5 centimeter, that is 45 centimeters square, and that is will be equals to 45 into 10 raised to power minus 4 meters square. Mu we can calculate from mu naught into mu r. Have they given us the relative permeability? Yes, it is 1500, and this value everybody should know, into 10 raised to power minus 7. So in this way we can calculate R1, and the value of R1 will be, the reluctance one will be 127.3 kilo ampere turns per Weber. Now let's look at R2. R2 is the resistance in the center. So R2 is equals to length of the core, that is, I call it L2, divided by mu, it is the same, and area of the air2. So let's look at these values. What will be L2? We can see from here to here it is 25. From here it is 4.5, 4.5, so it is 34 centimeters. That is equals to 0.34 meters. Area of the center leg will be, its width is 15 and depth is 5, so 15 into 5, that will become 75 centimeters square, equals to 75 into 10 raised to the minus 4 meters square. Mu, again, it is the part of the core, so we will have this value. This will become equals to, R2 will then be equals to, R2 is, the value of R2 is 24 ampere turns per Weber. Now let's look at R3. R3 is our famous air gap, and for air gap we call it length 3 mu into area of air gap. So length of 3 we have given, this is 0.04 cm, that will equals to 0.0004 meters. Mu is actually mu naught because it is air gap, and the area of the air gap, we have fringing effect here. So we have the area of the center part of the core is 75 centimeter, but due to fringing we have an increase. This will become 78 centimeter, or you can write 78 into 10 raised to the minus 4 meters square. So the value of R3, that is the air gap, will then become R3 equals to 40.8 kilo ampere turns per Weber. And finally we are at the R4. It is this side, and this length will be similar to R1. So this is L4 mu over that side. This length will be similar to L1, and it is actually replica of L1, or everything is similar to A1, and so this will actually become, R4 is actually same as R1, that is 127.3 kilo ampere turns per Weber. Now we have all these values. So can we calculate? Yes, we have R1, we have R2, R3, R4. Again, you should be very careful in calculating the values. This is a large equation. You can make mistake. So the value of RT will then become, solve this equation, 170.2 kilo ampere turns per Weber. This is the value of the total reluctance. And now we have this. Can we calculate the total reluctance? Yes, we can calculate the total reluctance. Yes, so we can calculate the total reluctance by the equation. Total reluctance is actually the flux on the left side of the core. Here the flux is total reluctance, and it will be the same in the reluctance R1. So we can calculate flux total is actually flux at the left side of the core equals to F divided by R total. And F, can we calculate F? Yes, F equals to Ni, and we have 200, and they have also given us the current I. Yes, here it is. They have shown it. Here it is, the current I, 2 amperes into 2. So we have 400 ampere turns. So we have 400 ampere turns divided by total reluctance, 170.2 kilo. So the total flux and the left side of the core will be then equals to 2.35 milliwebers. Yes, so now what is the flux? What flux exists in the 3 legs of the core? So in the left we have calculated this much flux is flowing. Now to understand the next part, I would like the students to remember the current divider rule, because here in this circuit actually what is happening, what you have studied similarly, this is flux of T this is flux here, and it is getting divided into 2 branches. This is similar to a total current I and I1 over I2. So if you can recall your memory, if we have a circuit like this and it has 2 branches, R1 and R2, and a current IT is flowing. Here we have I1, here we have I2. So the flux divider rule states that the current in any branch, for example, if I want to calculate current I1, it is actually equals to the resistance in the second branch, R2, into total current IT divided by total impedance R1 plus R2. This is actually known as current divider rule. So if in any branch you want to calculate the current, so I was calculating I1. So the impedance of the parallel branch into the total current divided by I2. So what will become for I2? The impedance of the parallel branch, I2 is flowing through R2, but here will be R1 into IT, total current divided by the sum of R1 plus R2. Okay, this is known as current divider rule, and it is very commonly used in our circuits. So actually now if we apply current divider rule, now let's look at our circuit, and if we want to apply current divider rule here, as I have explained you, so what will become? What should be flux in the center? That is equals to I1. So flux in the center, flux center should be equals to the impedance of the parallel branch, that is R4, into total flux, that is coming here, total flux, divided by total R2. This is same, this adds up, R2 plus R3 plus R4. This will give us the flux in the center branch, this equation. So I can calculate flux in the center branch is equals to flux in the center branch will be equals to R4 into flux T divided by R2 plus R3 plus R4, and this will become 1.56 milliwebers. Now what about flux in the right side? So again, if we can calculate, actually flux on the right side is flux T minus flux center, or if you want to practice your current divided rule, let's try to see what will be the flux right side, this flux here. So this will be, let's make some space, flux right equals to the impedance on the parallel branch, that is R2 plus R3, into flux of T, total flux, divided by the sum of both the impedances, reluctances. So this will become flux. So either you can calculate flux right like this, or you can calculate flux right like this, R2 plus R3 into flux of T divided by R2 plus R3 plus R4. So the value of this will become 0.79 milliwebers. So this is how we have calculated. We have solved the first part of the question, that was this has been the first part of the question, that was calculate three legs of the core. What is the flux density in each of the legs of the? So flux density you can calculate very easily. Let's look at here. So if you want to calculate flux densities, so in the left side we have the flux we have calculated flux left divided by the area of cross section. It will, how you calculate the area, that will be on the left side 9 centimeter into 5 centimeter, that is 45 centimeters. Similarly, in the center you have calculated flux center divided by area of the center. How will you calculate? It is 15 centimeter into 5 area of cross section. Flux you have calculated, and for the right side it will be flux right side that you have calculated divided by area of the right side. So what will be the area of the right side? It is 9 into 5, 45 again. So you can calculate all these values. You have so this will become 0.55 Tesla, 0.208 Tesla, and 0.176 Tesla. So that's how this question can be done. Hope it helps. Thank you. Assalamu alaikum.